Hi everyone, I am SS Kiran. I would like to discuss about semiconductor physics. Subject name is electronic devices and circuits. Previous video I have discussed about introduction of subject, justification, name and types of materials like insulators, semiconductors, metals. Okay, then classification using energy band diagrams, the definition of mobility and conductivity. Right. In this video, I will be discuss about electrons and holes in intrinsic semiconductors and extrinsic semiconductors. The next topic, drift and diffusion. Yes. Before going to the explanation, I will give some brief explanation about classification of semiconductors. Yes. Semiconductors are categorized into two types. One is intrinsic semiconductor, extrinsic semiconductor. Intrinsic semiconductor is also called pure semiconductor, right? Extrinsic semiconductor is also called impure semiconductor. These extrinsic semiconductor again classified into two types. One is N-type extrinsic semiconductor, P-type extrinsic semiconductor. Yes, now some theory, just you have to listen, you can understand. Some of the valence electron may acquire sufficient energy to enter the conduction band. See here, I will show one diagram. This is the energy band diagram of the semiconducting materials. See here, some of the valence electrons may acquire sufficient energy. I will draw here some of the valence electrons to enter into the valence conduction band for to conducting the material. See here, okay, valence band electrons may acquire sufficient energy to enter the conduction band to from free electrons under the influence of electric field. Okay, these electrons constitute electric current. Absolutely. So these electrons constitutes electric current, right? So again I will tell you, some of the valence electrons may acquire a sufficient energy to enter the conduction band to from free electrons, right, to free electrons under the influence of electric field. These electrons constitutes some electric current. Okay, assume, okay, a missing electron in valence band. There is a two bands. See here, there is a two bands. One is a valence band and second one is conduction band. In this missing of valence band, the missing of valence band leaves a vacant space, leaves a vacant space. This which is known as hole. Now there is a two particles here. One is electrons and vacant space, that is called hole. Holes are contribute the electric current, right? Holes are contribute the electric current. This is some introduction about intrinsic and extrinsic. So how extrinsic semiconductors are prepared, how N-type material formed, how P-type material formed, we can concentrate later discussion, right? Now, so our concept is electrons and holes in intrinsic semiconductor. So what is the other name for intrinsic semiconductor material? That is nothing but pure semiconductor. Pure means itself, its name indicates number of free electrons and number of holes is equal. So nothing but pure semiconductor or intrinsic semiconductor. Actually in chemistry, in some elements concept, there is a three categories, that is trivalent, tetravalent, pentavalent. Okay, trivalent elements are third group elements, tetravalent elements are fourth group elements, pentavalent elements are fifth group elements. Okay, coming to tetravalent group elements, fourth group elements have in the valence band side, there is a 4 valence electrons. What are the tetravalent elements? Carbon, atomic number 6, silicon, atomic number 14, germanium, atomic number 32. These three, okay, there is so many group 4 elements in the available. Okay, especially we can concentrate only these three fourth group elements. Those elements are carbon, silicon, germanium. These three elements we can call it as a pure semiconductor materials. See this crystal structure, you can understand. This is the germanium. What are the group 4 elements? Silicon, germanium. Okay, this germanium having 4 valence electron at the outermost orbital. Okay, see here, you can understand. I will show. This is one electron, this is one electron, this electron, this is the valence band, right? Okay, nothing to concentrate everything here, just out points, that is enough. Okay, in this intrinsic semiconductor, the number of electrons and the number of holes are concentration, everything is equal, right? See this diagram, you can understand the bond incomplete. So right, this is the one previous one, this is the germanium structure, right? Now our main concept is, in a pure semiconductor, the number of holes and number of free electrons, the thermal agitation constitutes to produce new hole electron pair, which this disappear as a result of combination. This is our main important concept. Electrons and holes in intrinsic semiconductor, simply you can write this only one point. The group 4 elements, those are carbon, silicon, germanium. They have 4 valence electron at the outermost orbital, okay, which constitutes the current by using electrons and holes. Okay, the number of electrons is equal to number of holes is nothing but the intrinsic semiconductor. Now coming to extrinsic semiconductor, just to adding some impurities to pure semiconductor, it simply converts into a extrinsic semiconductor. Then you can concentrate one more point. Actually there are 3 types of group elements. The first one is group 4 elements, those are carbon, silicon, germanium, right? These are also called tetravalent elements. These tetravalent elements covalent bond with pentavalent, like group 5. You can expect n-type material. Okay, again I will tell you, extrinsic semiconductor again classified into n-type material and p-type material. Okay, these two materials are very useful to design all electronic components by using only these two materials. That's why you have to concentrate how to make, how to design, how to happen of these two materials. Just you have to concentrate more and more. Okay, extrinsic semiconductor is also called impure semiconductor. To adding impurities to intrinsic semiconductor, it forms extrinsic semiconductor. Adding impurities is also called as a doping. It's a 2 marks question. What is doping? See here, it becomes impure or intrinsic semiconductor. The process of adding, I will show here, I will underline the point. The process of adding impurities is known as the doping. Okay, I will tell you total sentence. Due to the poor conduction, some of the room temperature, intrinsic semiconductor as such, it is not useful. The electronic devices, absolutely, due to poor conduction, intrinsic material is nothing but some pure conduction, means it looks like it's acting as an insulator. Okay, not useful the electronic devices. If you want to design electronic device, definitely you can concentrate semiconducting materials. In that semiconductor materials, you have to take extrinsic semiconductor material. In that extrinsic semiconductor, you have to take either n-type or p-type. By using these two materials, you have to design all type of electronic components. Okay, and the room temperature, and that's why I have mentioned here, due to poor conduction at room temperature, the intrinsic semiconductor, it is useless. If you want to design any electronic device, you have to use this extrinsic semiconductor, so that the intrinsic semiconductors becomes a impure or intrinsic semiconductor. This process of adding impurities is known as doping. the amount of impurities added is extremely small. So, say 1 to 2 atoms of impurities or 10 to the power of 16 intrinsic atoms. Okay, now what is our question? Uh, Pure semiconductor to adding impurities is nothing but doping. To do doping, we can expect two type of materials. One is N type of material and second one is P type material. Again, we will come back into the group 4 elements. Our group 4 elements are carbon, silicon, germanium. These are pure semiconducting materials. Just simply you have to covalent bond with pentavalent elements. We can expect N-type semiconductor. I will tell you the definition. What about P-type elements? Okay, group 4 elements covalent bond with trivalent or third group elements like boron, aluminum, gallium. So what about tetra means? Tetra means fourth group elements, carbon, silicon, germanium. What about pentavalents? Pentavalents are also called fifth group elements, nitrogen, phosphorus, arsenic, antimony. Okay, in nitrogen atomic number 7, phosphorus atomic number 15, arsenic atomic number 33, antimony atomic number 51. The trivalent elements are boron, aluminum, gallium. So again I will tell you, just tetravalent elements are covalent bond with pentavalent, we can expect N-type material. Tetravalent group elements are covalent bond with trivalent elements, you can expect P-type of material. Right, now we will enter into the definition. A small amount, I will underline here, a small amount of pentavalent impurities such as arsenic, antimony, phosphorus is added to pure semiconducting materials like crystal is to get semiconductor. Right. Okay, I think you can understand. Very simple, nothing to concentrate everything, just you can concentrate only basics. Okay, germanium atom has 4 valence electrons. See here, germanium electrons have 4 valence electrons, and run here this is antimony. Okay, 5 1 1 2 3 4. Okay, some valence is the 5, right? This is covalent bond with the germanium material. We can expect the what? N-type material. See here, loosely bond, right? Okay, in this N-type material, what is our concept? Electrons and holes in extrinsic semiconductor. That is our concept. You have to write the major point, that is called, in N-type semiconductor material, due to donor impurities, due to donor concentration, we can expect some charge carriers. Okay, in N-type semiconductor, the majority charge carriers are electrons. Okay, the majority charge carriers are electrons. The minority charge carriers are holes in N-type semiconductor. Okay, I will underline here what is donor impurity. Such pentavalent are called donor impurities because it donates one electron for conduction, giving an electron for a conduction. So very important. That's why in N-type material, the majority charge carriers are electrons. Okay, and the minority charge carriers are holes. Now coming to the P-type semiconductor. Very simple. The P-type group elements are boron. See here, boron having 3 valence electron. I will show here 1, 2, 3. Okay, these 3 are trying to covalent bond with pure material, that is called germanium. So here what is the definition? In this P-type semiconducting material is nothing but that is the adding impurities. What type of impurities? Acceptor impurities. So here I will show the see here I will show the definition. Underline the point. Okay, a small amount of trivalent impurities such as aluminum, boron is called pure semiconductor to get the P-type semiconductor. Very important. For N-type to small amount of pentavalents in p type, a small amount of trivalent to what? Pure semiconducting materials, right? That is called that is nothing but the p type materials, right? See here structural diagram also. Okay, these positively charged holes increase the conductivity of p-type semiconductor. Trivalent impurities such as boron is called acceptor impurities. See here underlined one, acceptor impurities for p-type semiconductor, donor impurities for n-type semiconductor, right? Now coming to the charge carriers, right? Majority charge carriers of p-type semiconductor are holes. Minority charge carriers are electrons. This concept is very important. Again I will tell you, tetravalent covalent bond with trivalent we can expect p-type, tetravalent covalent bond with pentavalent we can expect these n-type materials, right? This is a simple concept, I think you can understand, right? Now our concept is drift and diffusion currents. Okay, so before going to the these two currents, first of all we can concentrate on what is current. Yes, a current is defined as flow of electrons. What is current? It's a flow of electrons. What is expression for current? I is equal to dq by dt. Okay, a charge can move with respect to time from one place to another place. That flow is nothing but the current. Any charge, let us take, you can charge, there is a two charge particles, one is electrons and second one is holes. Electrons are always trying to move from one side to another side, it constitutes some current. So moving of the charge carriers is nothing but the what? Moving of the charge carriers is nothing but the current. Okay, I will tell you the definition. So these currents are categorized into two types. One is drift current and another one is diffusion current. What is the major difference between drift current and diffusion current? For a drift current, you have to apply electric field. For diffusion current, without applying electric field. You know, the last session I have discussed about J is equal to sigma E bar and Vd is equal to mu E bar. What is Vd? Vd means drift velocity. Vd is equal to mu E bar. Mu means mobility. E bar means electric field. Okay, now we will enter into the first of all we will enter into the drift current. See here the definition. When an electric field is applied across the semiconducting material, you know, electric field is applying means what? Indirectly you can apply the voltage. If we apply the voltage, all charge carriers or electrons are trying to move within a velocity. That velocity is nothing but drift velocity. Okay, that velocity is nothing but drift velocity, which is equal to the produces of the mobility. That's why we can express Vd is equal to mu E bar. Okay, I will show the exact definitions. Okay, first the currents are classified into two types. One is drift current and another one is the diffusion current. First we can start with the drift current. When an electric field is applied across the semiconducting material, the charges carriers attain certain drift velocity Vd, which is equal to the product of mobility and charge carriers and the applied electric field. Already I will tell you in the previous section, I will draw the expression Vd is equal to mu E bar. Okay, see here, Vd is equal to mu E bar. This drift velocity is proportional to the product of mobility and electric field. Okay, right. Now see here, when an electric field applied across the semiconducting material, the charge carriers attain certain drift velocity Vd when is equal to product of mobility of the charge carriers and applied electric field intensity E bar. Now holes move towards the negative terminal, battery and the electrons. So one more important point here, very important concept. Let us take one example. See, if there is the electrons, electrons, electrons and holes, 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 just you can apply the power supply. Okay, now these electrons are always trying to attract this negative terminal. These holes are always trying to attract this positive terminal. Okay, right. These electrons are trying to repel this negative terminal. The electrons are trying to repel this negative terminal. These holes are trying to repel this positive terminal. Right. Now see here. What is a drift current? Again I will tell you. The holes move towards the negative terminal of the battery and electron move towards the positive terminal. The combined effect of movement of charge carriers constitutes current known as drift current. See here, I will draw once again. Okay, this is the some material. This material having electrons, okay, and holes. So give power supply, right? Okay, this is negative, this is positive. These holes are trying to attract this negative terminal. These electrons are trying to attract this positive terminal. It constitutes some current. This current is known as drift current due to drift velocity. What is expression? Jn is equal to q into n into mu n into E bar. So units of Jn is equal to ampere per centimeter square. Okay, let us take drift current due to n-type material. So we can call Jn is equal to Qn into mu n E bar. Okay, Jn is equal to sigma E bar. Sigma is equal to Qn mu n. The drift current due to p-type, simply we can write Jp is equal to Qp mu p E bar, right? If you want total current, p-type current plus n-type current, Jn plus Jp is equal to just adding these two equations. Again I will tell you what is drift current. To applying the electric fields, the combined effect of movement of the charge carriers constitutes a current is known as the drift current. Okay, what is N here? Number of free electrons per cubic centimeter. What is P here? Number of holes per cubic centimeter. Mu N, mobility of electrons in centimeter square per volt second. Mu P, mobility of holes in centimeter square per volt second. Electric field E bar, Q, charge of electron 1.6 into 10 to the power of minus 19 coulombs. Okay, this is the drift current. Okay, again I will tell the definition of drift current. Just movement of the charge carriers, when applied the electric field, it constitutes the current. That current is nothing but the drift current. Okay, now diffusion current. Without applying any external field, without applying any electric field, without applying any voltage, electrons are trying to move higher concentration to lower concentration. The moving of charge carriers, it constitutes some current. Without applying any electric field, electrons are trying to move higher concentration to lower concentration. Those currents are nothing but the diffusion current. So see here, absence of applied voltage. See here, I underline the golden point. Absence of applied voltage provided. Okay, provided a concentration gradient exists. So some concentration gradient means dou n by dou t or dou p by dou t. Those are called the concentration gradients. It is possible for an electric current to flow in a semiconductor even the absence of applied voltage provide a concentration gradient exists in the material. See here, you can understand the diagram. This is the higher concentration, this is the lower concentration. Electrons are trying to move towards like this. Okay, higher concentration to lower concentration without applying any the electric field or potential. Okay, from the region higher concentration to of lower I underline the point, higher concentration to the lower concentration, right? Now, the movement of charge carriers takes place resulting in a current called diffusion current. So, definition of diffusion current, the region of higher concentration or to that of lower concentration of the same type of charge carriers, thus the movement of charge carriers takes place resulting the current. Those currents is called the diffusion currents. So, what is the expression for diffusion current? Jp is equal to, for p type, Jp is equal to minus q into dp by dx ampere per centimeter square. This is for Jp. If you want to write Jn, minus q into dn by dx. See here, you can understand. Jn equal to okay, q dn dou n by dn by dx. Dn by dx means it is charge gradient, right? Concentration gradients. Those are the concentration gradients. What about dn dp? Those are diffusion coefficients. Okay, if you want the total current, Jp equal to q into p into mu p into e bar minus q into dp into dp by dx. For p type diffusion current, Jn means n type diffusion current. Now for a brief discussion about drift current and diffusion current, without applying any current, charge carriers are moving higher concentration to lower concentration. The movement of charge carriers is nothing but the diffusion current. Applying electric field, electrons are trying to attract to the positive terminal. Okay, electrons, holes are trying to attract to the negative terminal. This movement of charge carriers is nothing but the drift current. These electrons having some drift velocity Vd. Okay, this is nothing but the drift current and diffusion current. By writing these two equations, it's very important. You will get good marks in your under examination. So Jn is equal to Qn mu n e bar, Jp is equal to Q p mu p e bar ampere per centimeter square. For diffusion current, Jp is equal to minus Q into dp by dx, Jn equal to Q into dp by dp into dn by dx, right? Just if you add the currents, we get the total current also. Next video I will discuss remaining topics. Thank you so much. Thank you.